Hi there. Today we're going to talk about another type of analysis. It's called a regression, but we're going to start out by talking about a plot of some data. It's called a scatter plot. Correlation, which is a statistic that we're going to calculate, and then we're going to talk about causation again, which we've mentioned many times. All right. So we're talking about this kind of data. So here's my data set. I've got total runs and average attendance for the American League for the 2010 season. All right, so you can see we've got several teams, and here's how many runs they made over the entire season, and it's sorted by most runs to least runs. And then over here, we have the average attendance of the games. So, fair weather fans, we might expect that, the attendance might be higher for teams that score more runs. I mean, they're going to win more too. And so that's the kind of analysis we're going to do here. Now what we have here, I have two quantitative variables. And I want to know, does one, a variable, affect the other variable? This is a 1. Okay. So the first thing we're going to do is, in order to see, in order to look at relationships, I need to get a graph of that data. All right, so we're going to graph both the runs and the attendance at the same time. All right, and the way we're going to do that is with a scatter plot. And so with a scatter plot, it's going to have, I'm going to have an x-axis and a y-axis. And I have to pick, and what I want to do is say which variable is my x variable and which is my y. And I'm going to pick the y variable so that it depends on the x variable. All right, so in our question or our expectation, we think if you score more runs, then you'll have higher attendance. So we kind of think of attendance being a response to the number of runs. All right, so y would be the attendance, which would depend on x, and that should be, in algebra, we always write, that y is some function of x. All right, so we're going to use that same idea that y depends on x. So here we're going to say that since we want to know if, do runs affect attendance, all right, then my response variable or my dependent variable is attendance. So we're going to put attendance over here. And then I'm going to put runs down here. So the name of those variables, the y variable is called the response variable or the dependent variable. All right, because we think y depends on x. So here, attendance depends on runs. It's also called a response variable. Attendance is a response to runs. So more runs, the response would be more attendance. Fewer runs, the response would be fewer attendance. All right, so then the x variable, which is here would be the runs, so here I'll put that y is attendance. And then here, x is going to be my runs. And so runs here is called the independent or explanatory variable. And this doesn't have the same kind of independent definition that we've used in the past. All right, so it's just, if you call y the dependent, then this is the independent. So it's not that they don't affect each other. So this has a different connotation. than we used in the past. So, but explanatory, you could think, you know, runs, more runs explains why there might be more attendance. All right. So those are the types of variables we got. All right, so here's a copy of the graph. I have it there. I'm going to go ahead and show you in StatCrunch. All right, I've already made it. Get out of there. And so I can do this with graph scatter. I'll go ahead and do that. And so my X, we said that was the runs, and the Y was the average attendance. All right, and here is my scatter plot. Each of these dots represents one row. All right, so like this guy, that represents the New York Yankees. The X coordinate is 859. Right, you see 850, a little bit more. The Y coordinate is attendance, and that's a little bit higher than 45. So that's that guy. And then, you know, if I want to look at this guy, that's Los Angeles Angels. Their total number of runs was 681, so somewhere around there. And their attendance was right at 40. All right. So every one of these, so for each row, for each pair of data, this is paired data, but we're not doing a pair T. We have one dot on the screen. And you can see here, I kind of wrote that in here on the notes. And so I look at this, and when I see this, what I want to see is there a pattern going on. All right, so there seems to be, it appears, you might think, what pattern? As runs, when we have more runs, all right, so out here, I've got more points up in this area, all right, for the top. When I have very few runs, all right, so from here to here, you know, I've got all this data down here. And then when I get over here, I have more data up there. So it kind of appears that as runs increase, so does attendance. And then we're talking about on average. So not every point is going to fit that idea. But in general, if I look at, you know, what's happening on average at these different areas, so like if I looked in the middle, we might say, okay, around here, maybe it's, you know, that might be an average for these, here's an average, you know. So basically, as X is getting bigger, Y is getting bigger, all right? And so what we say, whenever we see a pattern like that, where as X changes, Y changes in some way, we say that there is an association. So that's what we call it. We say that you know, runs and attendance are associated. That just means there's some pattern. There is an association, all right? So an association just means, you know, as X increases, Y changes, and you know, the average Y also changes. Right, so if we see, you know, as I increase X, then Y is like either going up, down, or both, or whatever, then we say that X and Y are associated, or there is an association between X and Y. All right, so when we describe an association, there's three things that we talk about. Its form, its direction, and its strength. So the form, this is the overall pattern. What is the shape of that pattern? All right, and when I say overall pattern, I'm talking about a curve. So if I was to draw a curve through the middle of these points, right? So maybe I would say, okay, over here, it's kind of down here in the middle, you know, so it kind of looks like maybe on average, it's this shape of this curve, that's a line, right? So for the runs versus attendance, we would say above, right? We would say the form is linear. It's a line, it's a straight line. And really that's, for this particular class, all we're wondering is it linear or not? Okay, so above, yeah, we might say, okay, on average, if I take a curve through the center of the points, it looks like it might be a line. Not all curves are linear, right? Or not all associations are linear. I might have something that looks like this, you know? You know, we've seen, well, we've looked at, if you guys have looked at the news at all, we have, here's the day, all right? And then over here we have, you know, number of cases. Right? And so it started out real low. So if I draw a curve, if I draw something through the middle of those points, this is curved. This is not linear. Okay. Next, all right, so I've said, okay, this guy is linear. I'm going to go ahead and write that right here. This is a linear association. All right, the direction tells you what's happening. What I said is x increases, y changes. Well, does it go up or down? So this one is actually either positive or negative. Positive, this is as x increases, so does y. This is positive. It's not linear, but it's positive. This guy is also positive. Not everything that's way. All right. Some relationships are negative. Negative, this means as x gets bigger, as x increases, y decreases. So I might have something that looks like this. All right. This guy's linear in form, but it has a negative direction. Now strength is the third thing. Strength is related to how close, you know, it's like how close to the points fit the line or the curve. The form. All right, so we might say they might have a weak association. Their strength is weak. Sometimes we have moderate, strong, very strong, and we'll talk about different, you know. This guy right here, that's very strong. The points are almost really close to the line. This one's pretty strong too. That's very strong also. The points just, I mean, because it fits the curve. It's not a line, but it fits the curve. So this is also very strong. Now this guy, the points can be pretty far away. Now you might be tempted to say it's weak, but because, I'll show you a weak association in a minute. But because it's clear to me that this relationship exists. And one of the ways I know it's clear, if I look up in this triangle area, there are no points in here. All right, that kind of lets me know, yes, there is this relationship. All right, so I can see, because of what's not there, I know that, okay, that my relationship's going on in this area. All right. And so because of that, this actually has a moderate association. When we say something's weak, it means I don't see an association. As x increases, the weak kind of means as x increases, nothing is happening to y. I'll show you one of those later. All right. So let's look at this one. We'll describe it. All right. So here, the form is a curve. It's not linear. The direction, it's different, okay? So maybe, you know, from here to here, on the left side, so when the baking temperature is less than 350 degrees, it seems like it's positive. So it's positive on this range and negative on this range. So here's the direction, it's positive for X less than 350 degrees. And then it's negative for X is greater than 350 degrees. So it's just different for different ranges of X, right? And this is a score based on a baking temperature. So it seems like the higher scores are up near 350 degrees. So maybe whatever we're testing, you know, we're saying, well, what's the best temperature? It looks like around 350 is what you would want to cook this thing at in order to get the highest score, whatever that means. All right, so let's kind of look at these examples and say, okay, so basically here, this number 1 here, what's happening? As X increases, what's happening to Y on average? All right, nothing. It's like the range, you know, the spread of Y is about the same, all right? And you might be tempted to say this is a linear, but it's not. It's really, there's no association, all right? So form, no association. So we're not going to have a direction, and we're not going to have a strength. This is just no association. This is, or I might say this is a weak. Maybe. So there's no direction. I might say, well, this is a weak association. But I wouldn't even say weak. I would say none. There is none. As X increases, Y staying the same. So Y doesn't depend on X here. We'll talk about that when we do some tests. We're going to test if Y depends on X or not. All right, number 2, all right, is form is linear. So this is linear. And as X increases, so as I go to the right, X increases as you go this way, Y is 1 up. So this is a positive association. And this is a very strong association. All right, 3, it's not linear. It's curved. All right, so 3, this is a curve. It's positive. It's still, as you know, as you go to the right, it's going up. Right. And then the points, they're pretty strong. I'm just going to say strong as opposed to very strong. All right, so this is still a strong association. And then 4, this is, if I draw a curve through it, that's a line. So this is linear. It's, as X is getting bigger, as you go this way, Y is getting smaller. So this is a negative association. And this is a very strong association. Okay. Correlation. Correlation is a statistic. And remember what a statistic is? Yeah. It's a calculation from data. All right. So all right, so we're going to use those 2 columns of data, those 2 quantitative variables, to come up with R. All right, and it measures the direction and the strength of a linear association. Okay, so that's what it does, and like I said, it's R. All right, so R is a statistic, calculate from data. All right, so it's only appropriate for linear association. So basically it is saying how linear are you? So when things are curved, like this guy right here, then it is not appropriate to calculate R here, because it doesn't make, because it's curved. I mean, you say how linear is it? It's not linear, it's curved. All right, so basically here I'd definitely want to calculate R for that guy and R for this guy. And I could measure R for this guy, but it wouldn't really tell me. It would just tell me, well, we'll talk about what that means. All right, so it's only for linear. So if the scatter plot is curved, all right, then don't calculate R. Okay, so what does R look like? R goes from -1 to 1. All right, so R can go anywhere from -1 to 1. If it's positive, so if it's, if R is positive, that indicates that X and Y have a positive association. Meaning, the pattern's going up. It goes right. If R is negative, then X and Y have a negative association, meaning that, as X increases, Y is going down. All right, so then so like I said, so the sign tells me what the direction is, if it's positive or negative. Now, the magnitude, that's like the absolute value of R, that's the value. So if R was -0.9, the magnitude would be 0.9. The sign would be negative and the magnitude would be 0.9. So basically anything near 1 or -1 is very strong. And anything near 0 means no association. All right, so this is where I was saying that where this guy, if I calculated R on this guy, then R would be near 0. And R, so we'd see, oh, it's near 0. That means there's no association, or it's not linear. All right, and I put 5. That should have been 0.5 or -0.5. All right. So if it's near 1 or -1, it's very strong. And if it's near 0.5 or -0.5, it's a moderate. So if we were guessing at our, we said this was moderate, then we would think R is around, and it's positive, so we say maybe around 0.5. Now it might be 0.6 or 0.4. I mean, it's, it's hard to guess R. Unless it's very strong. Like this guy right here, if I saw something that looked like that, I would guess that R would be -0.99, because it's like close, but its direction is negative, but its magnitude should be almost 1. This is almost an exact straight line. The curve, it doesn't make sense to calculate R. It doesn't make sense to calculate R. It wouldn't make any sense. All right. Okay. So, and so then if you get something that's like a 0.8, you might call that a strong, or even a 0.7, you might say this is a strong association. Something that's 0.9, you might say it was very strong. So that's kind of where that comes in. All right. So again, for runs versus attendance, since it's moderate, then we think, okay, R is near 0.5, as a rough guess. But we can calculate it in StatCrunch by running what's called regression. And so R is part of an analysis of 2 quantitative variables. It's called simple linear regression. So we're going to run stat regression, simple linear, and then we're going to pick our X and our Y axes. Kind of like we did for our scatter plot. So let me get into that. So I'm going to have stat regression, simple linear. And we said the X, that's our explanatory variable, that's runs. We think runs explains what's happening to attendance. And so when I do that, it spits out a lot of stuff. Gives me a lot of things. I kind of list the variables I chose. But down here you see R, correlation coefficient. So sometimes when people say correlation, they call it the correlation coefficient. But that is 0.54. All right. So when I ran this, R equals 0.54. So this was a good guess. And so this, because this is near 0.5, it tells me, that I've got a positive, moderate linear regression. I should always look at the graph though, not just calculate R and then let it tell me something, because I might, if I don't look at the graph, one of these curved guys might get me this calculation. So I want to look at the graph, make sure it's linear, and then decide if calculating R is appropriate. So let's talk about some properties of R. Okay, R has no units. All right, so this 0.54, it has nothing to do with runs or people or none of that. All right, so basically, if you looked at the calculation of R, which we're not, the calculation involves z-scores. Z-scores for the x's and z-scores for all the y's. All right, so I would calculate a z-score for every x and a z-score for every y. And z-scores have no units. So when I have calculations involving things with no units, then there's going to be no units. All right. R is not affected by rescaling or switching x and y. So if I switched attendance above was in thousands of people. If I switch that, I said, oh, let me just switch it to attendance in people. Just in people. If I changed all my y's so that they were in thousands instead of, or not in thousands, but in just regular people, R would say the same. All right, so if I rescaled, if I had something in temperature in degrees Fahrenheit and I turned it into degrees Celsius, R would say the same. By the way, the z-scores would all stay the same. So Z had the same property, that rescaling doesn't change your z-scores. It also says if I switch x and y, so if I decided, that I'm going to make attendance my x and runs my y, R would still be the same. So switching the x and y axis does not change R. All right. Another quality of R is sensitive to outliers. Now we talked about a few things that are sensitive to outliers. If we're looking at one variable at a time, then the mean, that we said y bar and s, the sample mean and the sample standard deviation are also sensitive to outliers. Right? And in fact, those y bar and s are used in those z-score calculations. All right, so the z-score for each of those will be the value minus the mean divided by the standard deviation. But basically what goes on, again, this R is a measure of how linear things are. So let's say I had some data points that look like that. All right, and I think, oh, maybe it's linear. All right. And then I said, well, that could be, a moderate linear relationship maybe. And let's say all of a sudden I said, oh, wait, no, I got one more point and it's right here. All right, so I thought maybe something was going on here, but now, so this guy, if I add this guy, it makes the graph less linear. All right, because now if I'm trying to fit a curve, I got to involve that guy too, and he's so different from the rest of the points. So I don't know what to do with it. Anyway, so basically this guy would make it less linear and it would make the magnitude smaller. So this would make, you know, R smaller, closer to 0. All right, so again, let's go over here. I got the same kind of points here, all right? And I'm like, yeah, it's you know, moderate. Now, if I stuck a point, I said, wait a minute, I got one more point, it's out there. All right, now this point is like, oh, okay, I'm gonna, you know, create a curve through the points. Now, oh, look, it looks like that. Now it makes it really look linear. So this guy is gonna make the graph look more linear. Now this will make ours bigger in magnitude, closer to 1 or -1. All right, so different kind. So this one, when it's totally off the line, is gonna make R smaller. If it's right on that line, it's gonna make R bigger. All right, so where maybe if I didn't have this point here, if I ignored that point, I just had these, maybe R is 0.4 or 0.3, it's weak. But if I had this one, now it's 0.6. So it increased R a lot because this point makes it look like, oh, look, I've got a linear relationship. All right, so outliers have a huge impact on R. Okay, so here's an example of 4 scatter plots, and they've given us 4 different values of R that we should match up to these scatter plots. So the first one, all right, this is linear, and it's negative, and it's very strong. So I would expect an R near -1. All right, so that's probably going to be this one. So this guy is R equals -0.977. All right, this one is linear, positive, and I would say it's strong. All right, this guy is not linear. I shouldn't be calculating R. Positive, and 4, and it's like I would say that's a moderately strong. All right, so whoa. Okay. And this guy, no association. All right, so for this one, I would think R should be near 0. And this one, R, I'm thinking should be around 0.9. And this one, it's not, this should be something else. So this, okay, so we said this one's that. So near 0, this -0.021, that's going to be this guy. The 0.951 positive, that's going to be this one. So the last one, this is R equals 0.736, which is, who cares, right? It doesn't matter because it's not linear. Okay. Last topic, I want to talk about correlation versus causation. And I'm going to make this big. This is important. All right. Correlation between 2 variables does not prove that one variable causes the other variable. This is important. Just like what we've been doing in the past, we said that observational studies do not prove causation. The same is going to be true here. All right, so over here I've got just some an example. All right, so if we were looking at different cities in the United States and we counted the number of churches and the number of liquor stores, we would see a very positive linear association. All right, now why is this happening? And the question is, I mean, do churches cause liquor stores? Is that why there's so many liquor stores? So I've got a city, it's got a bunch of churches, and then people don't like to go to church and they turn to drinking. All right? No, that is not the case. In fact, I could switch it. I can make this the liquor stores over here. I can make this the number of churches. I would still have this positive linear relationship. And now it's like, well, do churches cause, or do liquor stores cause churches? All right. Neither of those is true. Okay. There's a hidden variable. We've talked about this before. And it tells us, it's called a lurking variable, which causes both of these variables. So it affects both these variables and then affects the relationship between them. So why would you have more churches, you have more liquor stores? All right, so the lurking variable here, which is a variable we're not looking at in the graph, but explains the graph, would be population. Okay, we'll make it population size since we have another definition for population. So if I have a city that's a large city, I'm going to have more liquor stores and more churches. All right. So because I see the relationship, I see this big linear relationship, I cannot just imply, oh, that it must be causal. All right. The same over here, if I went to, got some data on fires, and I counted the number of firefighters that show up and the damages to the house, this is also going to be a very low. What? A very strong linear relationship. All right. And so we're still going to have this linear relationship. So are firefighters causing damages to the houses? What's the lurking variable here? What's the variable that would cause more firefighters to show up and cause more damages? All right, that would be the size of the fire. So if I have a big fire, then they're going to call in more firefighters and there's going to be more damages. All right. So whenever I see a relationship between the two variables, I may want to jump to the conclusion that it's causal, but I should not do that. And we found in previous studies that you cannot prove causation with an observational study. And here I'm observing fires, I'm observing cities. So unless I'm doing an experiment, which is where I would control the x-axis, I'd say here's, I'm gonna set up x is equal to this, set up x equals to this, and then see what y is. If I'm not doing that, then I cannot say that it's necessarily causation. If I go back up and look at my scatter plot of attendance and runs, right? All right, so we were asking if runs cause attendance, right? And so we did find that the more runs you have, the more attendance you have at the games, but it's not necessarily a causal relationship. It could be that the runs themselves are not what's causing attendance. There could be other variables that would cause you to have more runs and more attendance. All right, so I'm not saying that having more runs doesn't increase attendance. It's likely to do that. But the relationship I see here does not prove that getting more runs is going to cause attendance. In fact, I could switch these and make attendance on the x-axis and say, okay, let's make this attendance. then over here, I say, okay, this is runs. I would still, I mean, my graph would change, but it would still be a positive linear relationship. And then it would say, oh, if I have more attendance, that would cause more runs. And there could be some truth to that. It's like maybe you get more attendance, you get more cheers, and so the players respond to that. And so there may be some truth to that, but the relationship doesn't tell you that. So what the relationship tells you is there is a relationship. So when I see the graph, it's like, okay, there is a relationship between runs and attendance. Is it causal or not? I don't know. I can't, and I won't be able to tell from this relationship. In fact, there's no way to set up an experiment to say, okay, let's have a team score this many runs to see how much attendance they have. It's impossible. Now, what's a possible lurking variable? What could affect attendance and what could affect runs? Money might be a lurking variable. Maybe I get more money, I get better players, I get better advertising, so I'm getting more attendance and I'm getting more runs. So that's one possible lurking variable, but I don't know. But I cannot say that the runs are causing the attendance or that the attendance are causing the runs. I can never do that. All right, that is it. I'm done talking about correlation, and then my next video will be on linear regression. We'll be finding what's the best line to fit this data.